So we are starting our next goal, the second half of Unit 3. It still has to do with counting particles, but now we're going to be focusing on counting particles in chemical reactions, where previously we've been looking at just counting particles in like chemical species. We're going to start to shift towards chemical reactions. When we look at this and how it's going to be assessed, again, there are two separate goals. We have 3.2A, and then it's written here as 3.2C and D, but 3.2A and B are going to be our 3.2A quiz. And then 3.2C and D are going to be our 3.2B quiz. When we look at goal 3.2A, so those first three goals written here, shown here, we are looking at models of chemical transformations, explaining the relationship between the quantity of reactants consumed and produced in a chemical transformation, and then performing stoichiometric calculations involving the quantity of reactants and products. So we are going to continue carrying through with those mole conversions that we previously studied. Those are going to be a very large part of this 3.2 goal, the second half of this unit. So today's going to be kind of some of our background before we start talking about chemical reactions, type of reactions, the stoichiometry involved with chemical reactions. We need to understand some of how molecules and compounds look and how we write those. The first piece is talking about diatomic molecules. So when you look at your periodic table, we have all of these elements. Most of these elements exist as just monatomic. It's just that atom by itself. But there is a certain set of what we're going to refer to as diatomic molecules. And so if we dissect that word, diatomic molecules, that prefix di means two, atomic, obviously representing atoms. So two atoms. And then a molecule, remember, is two atoms that are covalently bonded together. And so these are going to be certain elements that always exist as a diatomic molecule. And it's these seven. It is hydrogen, nitrogen, oxygen, fluorine, chlorine, iodine, and bromine. When we look at these specific elements being a reactant or a product involved in a chemical reaction, and again, we're going to look at that in more detail coming soon, they always exist as a pair. We won't ever find just a hydrogen atom by itself as one single atom. It's always going to be bonded together with another hydrogen. And so hydrogen gas is always going to be written as H2. These first five, hydrogen, nitrogen, oxygen, fluorine, and chlorine, exist as diatomic gases in their elemental state. So at standard conditions, if we find fluorine will exist as F2 and it will be in the gaseous form. Iodine, I don't know why I wrote these backwards. Chlorine, bromine, and then iodine. Iodine is a solid at standard conditions, and then bromine is going to be a liquid. But no matter what the state is, these seven are always diatomic. And you will need to know these seven. Because when we start writing chemical reactions, if a reaction says hydrogen gas is produced, then you're going to need to be able to write that as H2 and not just an H by itself. There are a couple mnemonic devices that you can use to help you remember what these seven are. If you look up at the top in the highlighted periodic table, those seven, there's hydrogen, and then the other six. They kind of form the shape of a seven, and there's seven of them. Or these two mnemonic devices, there's Braun-Cliff, bromine, oxygen, hydrogen, nitrogen, chlorine, iodine, fluorine, or Brinkelhoff. So bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. Whatever method is going to work best for you, you do want to understand and know and be able to write these as diatomic molecules when we are using them in a chemical reaction when we get there. And again, it's just when they are by themselves as a single species. It's not when they're involved in another compound or some with other elements. It's just when they are by themselves in their elemental state, they are diatomic molecules. Okay. The rest of this lesson is going to be a review because it's something that we've talked about before. But when we get there, when we start writing chemical reactions, a lot of the reactions that we look at are going to involve reactants or products or species in that reaction that are ionic. Remember, we studied ionic bonding. It occurs between the attraction between a cation and an anion. Remember, cation being something that has a positive charge and an anion being something that has a negative charge. And these oppositely charged species or oppositely charged ions have an electrostatic attraction between their charges. And that electrostatic attraction brings those charges together and holds them together with that lattice energy. And that's what creates an ionic bond. We tend to use or think about an ionic bond being between like a metal and a non-metal. And that's the simplest form of an ionic bond. We're going to review how to write those ionic formulas when you know what your two elements or element and polyatomic ion are. You should be able to use your periodic table to predict their charge, the ionic charge that they form, and then how to put those together into an ionic compound. Because when we write ionic formulas, they represent that ionic solid, which is neutral. So looking at your periodic table, remember our periodic table is organized into these periods and these groups. And when we look at those main groups, it's those tall 8 columns. Those are our main groups 1A through 8A. The group number, the main group number, tells us how many valence electrons those elements have. Metals are the ones to the left of the staircase. Those are the shaded in ones on this particular periodic table. Metals have low ionization energy and low electronegativity, so they tend to lose their valence electrons, resulting in a positive charge. And so they lose based on the number of valence electrons they have. When we look at group 1A, the alkali metals, they're going to lose 1 valence electron, giving them an overall 1 plus charge. Group 2A are alkali metals. Group 2, or alkaline earth metals, have 2 valence electrons. They're going to get rid of those 2 valence electrons to form a 2 plus charge. Group 3A, looking at aluminum down, we ignore boron, but aluminum down have 3 valence electrons. They're going to form a 3 plus charge. Okay, so these are our metals, how we predict ionic charge for metals. If a reaction happens to involve a transition metal, it's those 10 B groups. If those are involved, we're going to talk about how to know what their charge is based on a compound that they're already in, or we would have to tell you their charge. But you should be able to tell us for main group elements what charge they form based on their location in the periodic table. And again, for metals, it's 1A2 or 1 plus, 2 plus, 3 plus. When we look at our non-metals, those are to the far right of the periodic table, to the right of that staircase. Remember that nonmetals have high ionization energy and high electronegativity. They're more likely to gain electrons to fill their valence shell. We tend to skip group 4A because they're kind of in the middle. They don't have very strong or high ionization energy or electronegativity compared to metals or nonmetals. And so they're least likely to participate in an ionic bond. So we're going to skip group 4A. But when we look at group 5A, these are nonmetals that have 5 valence electrons. In order to satisfy that octet rule, they're going to gain 3 electrons. And so that makes them have a 3 minus charge because, again, electrons are negative. And so if they gain 3 negatives, makes them overall 3 minus. Group 6A, your oxygen column, these have 6 valence electrons. They're going to gain 2 to fill their shell, and that causes them to form a 2 minus charge. And then our halogens, group 7A, have 7 valence electrons. They're going to gain 1 to fill their valence shell, giving them a 1 minus charge. When we look at group 8A, those are noble gases. With the exception of helium, they have 8 electrons in their outer shell. All of the noble gases have a filled valence shell, so they don't participate in ionic bonds because they're not going to gain or lose electrons because they're already stable. So these 1 plus, 2 plus, 3 plus, then 3 minus, 2 minus, 1 minus. Again, you should be able to use your periodic table and predict or determine what charge do metals and nonmetals form when they participate in ionic bonds. We then have to be able to use those charges to write ionic compounds. So again, in an ionic compound, it's a positive charge and a negative charge are attracted together. That electrostatic attraction creates that really strong ionic bond. And so given elements, you should be able to look at your periodic table, predict the charge, and then look at the charge of the cation and the charge of the anion and put them together to make an overall neutral solid. Oftentimes that will involve you using subscripts to make sure that the charge is balanced. Make sure that your solid represents a neutral ionic solid. When we look at this first example, sodium and oxygen. So looking at your periodic table, sodium is going to form sodium 1 plus. Oxygen is going to be oxygen 2 minus. When we put those together, we have a 1 plus charge and a 2 minus charge. We need 2 sodium ions to balance that charge, giving us an overall 2 plus and 2 minus, which cancel. Gives us an overall neutral ionic solid. So sodium and oxygen form Na2O. If you'd like to pause the video and practice these next few before I go through them, then you are perfectly welcome to, or just work them as we go through together. The next one is calcium and sulfur. Calcium is a 2 plus, sulfur is a 2 minus. Those charges do cancel each other out, so that forms calcium sulfide, or CaS would be the formula for that ionic compound. Magnesium and nitrogen. Magnesium is magnesium 2 plus. Nitrogen is nitrogen 3 minus. For those charges to cancel, we would be getting them both to 6 plus and 6 minus, so Mg3N2. Rubidium and phosphorus. Rubidium is a 1 plus, phosphorus is a 3 minus, so we need 3 rubidium ions for every phosphorus ion, so Rb3P. Magnesium and bromine. Magnesium is a 2 plus charge, bromine is a 1 minus charge. When we put those together, our formula is MgBr2 for magnesium bromide. Barium and selenium. Barium forms a 2 plus charge, selenium forms a 2 minus charge. Those charges cancel. They're 2 plus, 2 minus. It's overall neutral when we put those together. So BASE is barium selenide. And then the last example is aluminum and iodine. Aluminum forms an ion with a 3 plus charge. Iodine is a 1 minus charge. When we put those together, we get Ali3 for aluminum iodide. Your assignment is to practice in your packet. I know you don't have your packet yet, but I'm posting the worksheet that you would have gotten in your packet. And if you have access to a printer, you can print it, or you can just work it on paper. But working through the practice for this, the top is just background information. We are doing ionic formulas. We're less focused on the naming. We need to make sure that you can write formulas. This practice is a little simplified because I've already given you the charges for all of the ions that are involved. Notice that some of these are polyatomic ions. Remember, these are groups. They act as one ion, but they're on your polyatomic ion list on your equation sheet. So PO4, 3 minus. PO4 is one group, that's phosphate. And overall, it has a 3 minus charge. So you treat it as one group. If you need a subscript following it, like if you need 2 phosphate ions in a formula, put PO4 in parentheses and then the subscript 2. You treat it as one unit. And so you're just practicing writing the formula to show that these are overall balanced. But again, in reality, you should be able to tell me the charges for any of these that are just an element from the periodic table. And then also be able to use your polyatomic ion list on your equation sheet to figure out the charge of those, to recognize and figure out the charge of those polyatomic ions. This is your practice. Let me know if you have questions, but otherwise just work through writing the formulas for all these compounds, keeping in mind that they have to be overall neutral. Use parentheses when needed, subscripts when needed. Overall, no charges should appear in your overall equation.